everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to look at the condensation polymerization to form polyesters and polyamides, and then the acid and base hydrolysis of the ester groups in polyesters and the amide groups in polyamides. And then we're going to predict from addition and condensation polymerization of the repeat unit from a given monomer, the monomer required for a given section of a polymer molecule, and the type of polymerization. Now I'm going to quickly run through what a condensation polymer is. So condensation polymerization occurs when many monomers are joined together to form a long chain molecule called a polymer, and also a small molecule, and usually this is water or HCl. And we must have monomers with two suitable functional groups per molecule for a condensation reaction to occur. And we've actually seen some condensation reactions because we've seen the reaction between a carboxylic acid and an alcohol to form an ester. And this also forms water, and that's why it's a condensation reaction. Similarly, we've seen the reaction between an acid chloride or an acyl chloride and alcohol, and these react to form an ester and HCl. So this is also a condensation reaction. So now we're going to talk about polyesters. And polyesters are a type of condensation polymer, and they're formed from diols and dicarboxylic acids. And the reason why is that to form esters, we need an alcohol and a carboxylic acid. And so in order to get this ester group, C double bond O, to repeat over and over again, we need diols and dicarboxylic acids, because then we have the two functional groups on either end of each of these chemicals. And so, for example, we can look at ethane 1,2-diol. So we have OH and then CH2OH. So we have an alcohol group on either end. So we call this ethane 1,2-diol. And we have benzene 1,4-dicarboxylic acid, which looks like this. And then we have a benzene, carbon double bond O, and then OH. So this is benzene 1,4-dicarboxylic acid. These two chemicals actually react to form terylene, which is a polyester. So what I'm going to do first is I'm just going to write them both out again. So we have HO, CH2, CH2OH added with HO and then C double bond O, which is attached to benzene, and then OH, then added with another one of these HO, CH2, CH2OH plus dot 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 plus dot dot dot. What we're doing is we're removing waters. So we're removing this water here. So this water comes out in the condensation polymerization. And this water also comes out as well. And so on down the line. And so the polymer we form is one that looks like this. So we have O, CH2, CH2, and that line is just to indicate that it goes on. And then we have O, C double bond O, and then the benzene, and then a carbon and double bond oxygen, and then we have another oxygen, CH2, CH2O, and then dot dot dot. So again, we can say that. And so now you can see that we have these ester groups that are repeating. So this here is an ester group. And so is this one. And there'll be many more down the line. And this is why this is called a polyester. And we can actually work out the repeating unit of this, because what we do is start here, and then we just go along from left to right and see when we start to repeat ourselves. And you'll find that it's over here. And so the repeating unit for this polyester, is OCH2, CH2, O, C double bond O, and then a benzene, another carbon, and then a double bond O. And so this is our repeating unit for terylene. So now we're going to talk about polyamides. Now, polyamides are formed for a diamine and a dicarboxylic acid. And this is because normally to form amides, we need an amine and a carboxylic acid. So in order to get this amide link, this C double bond O NH, to be repeating over and over again, then we need an amine and a carboxylic acid. So we have two examples of polyamides. The first is nylon 6,6 and the second is Kevlar, and you'll need to know about both of them. So nylon 6,6 is made out of 1,6-diaminohexane and hexane 1,6-dicarboxylic acid. So we have NH2, CH2, and we have 6 of these, and then NH2. So this is our 6-diamine, diaminohexane. And then we also have hexane 1,6-dicarboxylic acid. So we have COOH, and then 4 of these CH2s, and then COH, and then O. So this is hexane 1,6-dicarboxylic acid. And these two react together to form nylon 6,6. And you'll need to remember these two chemicals that join together to form nylon 6,6. So again, what we do is we have the diamine and we have this dicarboxylic acid, and we have dot dot dot, and then plus dot dot dot. And what we're doing is, again, we're taking away a water, so we're taking away this, and this is removing a water. And so what we form as our nylon 6,6 is NH CH2 6 NH C double bond O CH2 4 C double bond O, and then it repeats, so we have NH and so on. And so from this we can see the repeating unit. So if we start here, again we scan through and see where it repeats again. And so this would be our repeating unit. And so the repeating unit would be NH CH2 6 NH C double bond O CH2 4 and then C double bond O. So this is our repeating unit for nylon 6,6. So one thing to note about nylon 6,6 is that in the lab the reaction goes much faster if we use a diacid chloride or a diacyl chloride instead. However, HCl is the small molecule which is liberated, so we get NH2 and then CH2 6 and then NH2 again, and then we have this diacyl chloride instead of the dicarboxylic acid. And so what we have now is that we have that this HCl is taken away, so it's liberated. And so we still form the same polymer, the same polyamide, which is the nylon 6,6. So we still form this N CH2 6, NH, C double bond O, CH2 4, C double bond O, and I've just drawn the repeating unit. So we still form this. Now we're going to look at Kevlar. So Kevlar is another polymer which is made from condensation polymerisation, and it's made from the monomers benzene 1,4-diamine and benzene 1,4-dicarboxylic acid. So we have NH2 and then a benzene, then a nitrogen, and then another 2 hydrogens, and added with this dicarboxylic acid, like this, plus dot dot dot, plus dot dot dot. And you can see that this is quite easy to remember because they're both based on benzene, and they're both on 1 and 6, both of the either the amine or the carboxylic acid groups. And so the 2 monomers for Kevlar are really easy to remember. And then what happens is that we liberate the waters, and so this water becomes liberated, and so on down the line. And so what we form is we have NH, and then we have this benzene, NH, C double bond O, and then we have another benzene, C double bond O, and then NH, and then we get another benzene, and then NH, C double bond O, and etc. So this is Kevlar that we formed. And so you can see that it's really easy to remember because we just have these amide groups, so these amide links separated by benzene. And if you're going to remember it as amide links separated by benzenes, you need to make sure that this swaps on the other side of the benzene. So on the left of this benzene here, we have the C double bond O first, and then this NH. But on the other side, on the right hand side of the benzene, we have NH first, and then C double bond O. So you need to make sure that you remember that. And so working out the repeating unit of this would be if we started here, and then you scan along to see when it starts to repeat. And so this section here will be the repeating unit. So we have the repeating unit is this NH benzene, and then we have the amide link, and then another benzene, and then a C double bond O. And so this is our repeating unit for Kevlar. Now we're going to look at the hydrolysis of polymers. So we can hydrolyze or break up polyesters and polyamides into their specific monomers by using acids or alkalis. And the products formed depend on whether we use acidic or alkaline conditions. So first we're going to look at the hydrolysis of polyesters, and we're going to use the example of PTT. And so basically what it is that if you think back to when we hydrolyze normal esters, so not polyesters, but just esters, if we hydrolyze it using sodium hydroxide, we form a salt of the carboxylic acid. So we form a carboxylate, and then we also form the alcohol. Whereas if we hydrolyze an ester with a H plus catalyst, so acidic conditions, we form the carboxylic acid and the alcohol. And so the first thing we need to remember is that polyesters are made out of dicarboxylic acids and diols. And so when we hydrolyze it, we either form the salt of the carboxylic acid, of the dicarboxylic acid, or the dicarboxylic acid and the diols. And so for this example, for PTT, what it looks like is we have C double bond O, and then we have a benzene, and then we have another C double bond O, then an oxygen, and then we have 3 of these CH2s, and then we have another oxygen. And so this is our polyester. And so first we're going to look at hydrolyzing with a base, so such as sodium hydroxide. And so one thing to note is we know it's polyester because of this group here. This is an ester group, and this repeats throughout the whole long chain molecule, and so that's why we call it a polyester. And so when we use sodium hydroxide, what we form is the salt of the dicarboxylic acid and also the diol. And so the salt we form is, we have Na+, and then we have COO-, and so this is attached to benzene. And then we have the same thing on the other side. So it's exactly the same as for when we hydrolyze esters, but this time we have a salt of a dicarboxylic acid rather than just the salt of the carboxylic acid. And we also form, and we actually have N of these because we've only drawn a small section of the polyester. And so we then form the diol. So we have N amounts of the diol, so HO and then CH2 3OH. But when we hydrolyze with H+, so how we name this is we first name the CH2 group first. So we have 3 carbons, so it's propane. So we have propane, and then we put the numbers in. So we have propane 1,3-diol. And so the key thing to remember is that in alkaline conditions, when we hydrolyze this PTT, we form the salt of the dicarboxylic acid and also the diol, compared to when we use acidic conditions, we form the dicarboxylic acid and the diol. And secondly, we're going to look at the hydrolysis of polyamides. So we need to remember that polyamides are made up of dicarboxylic acids and diamines. And so that means that this is what we'll form when we react it in acidic conditions. And in alkaline conditions, we'll form the salt of the dicarboxylic acid. So we're going to use the example of Nomex. And Nomex is actually used in oven gloves and in fire protective suits. So what it looks like is we've got C double bond O, then we have a benzene ring, and then another C double bond O, and then we have NH, another one of these benzenes, and then we have NH. So this is our polyamide. And we've actually also learned this as Kevlar. So Nomex is just another name for Kevlar. And so first we're going to look at the hydrolysis using a base, so sodium hydroxide, and this is going to be alkaline. And so we form the salt of the dicarboxylic acid. And so we form N numbers of this Na+, and then we have the COO-, and we have the benzene attached, and then the same on the other side. And then we also form N amounts of the diamine. And so we form NH2, and then the benzene, and then the benzene, and another NH2. So the name of this would be benzene 1,4-diamine. And when we hydrolyze it using a H+ and water, so this is acidic, what we form is N numbers of the dicarboxylic acid instead of the salt. So we have the carboxylic acid group, and then we have a benzene, and then we have another carboxylic acid group on the other side. So this is benzene 1,4-dicarboxylic acid, and we also form n amounts of, again, the diamine, so the same diamine as we had when we hydrolyzed it using sodium hydroxide. So you've always got to remember that when we hydrolyze these polymers, so polyesters and polyamides, we always form the same either diamine or diol. It's just the dicarboxylic acids which are different, because with the alkaline conditions we form the salt rather than the dicarboxylic acid. Now we're going to talk about how to identify the monomer or monomers of a condensation polymer. And so the best way to work out the monomers in a condensation polymer is to try and recognize the links formed by familiar functional groups. So what we can do is we can kind of form a table. So we have monomer number 1, and then we have monomer number 2, and then we have the polymer. So if we have a dicarboxylic acid, so we have HOCO, and let's just call this A. A can be anything. And then the second monomer is a diol. So we have this. I'll call this B instead. So this is a diol, and this is a dicarboxylic acid. Then what we would form would be this polymer. So we'd have carbon with a double bond O, and then A, carbon with a double bond O, and then O, B, and O. So this is the polymer we would form with these two monomers. And so this is what you would remember. So this is the kind of table that we would form. And the second, we would have a dicarboxylic acid, and this time we'll add a diamine, and so we'll have NH2, and this will form this kind of polymer. So we have C double bond O, A, C double bond O, and then so we have this amide link, and then B, and then NH. So this is our repeating unit for a polyamide. So the first one we form is a polyester, and then the second one is a polyamide, and we know this because this is an ester link here, and this is an amide link here. And then we have one more, so we have the one where we use amino acids, and so this is a dicarboxylic acid and a diamine. And this time, if we just have an amino acid, because it's got two groups on it already, we actually don't need two monomers. And then this is the amine bit of it. So because amino acids have a carboxylic acid bit and also an amine bit, we don't need two monomers to form a polymer. And so this also creates a polyamide, but its repeating unit is a bit different. Because we're only using one monomer. And so using this table, we should be able to see the different monomers which make up the polymers. So again, this is a polyamide or a polypeptide. And so this should help us if we've kind of got this table in our heads. And so the method that we use is first we start with the repeating unit, and then we break the linkage at the CO bond for a polyester, or a CN, or at the CN bond for polyamide. And then we add the components of water for each ester or amide link back. And so if we look at a quick example of just for a general condensation polymer. So we have carbon double bonded with an oxygen and then A. And then we have O, CO, C double bond A, C double bond O. And so you can see this is a polyester, because we've got this classic polyester, this ester group there. So if we had an ester that looked like this, the first thing to do is to start with the repeating unit. So the repeating unit is from here all the way to here, because after that it just continues to repeat. And then what we do is we break the linkage. So this is a polyester, so we break it at the CO bond. So we break it here. And then we add back the components of water. And so this will form, if we add water, we will form C double bond O, OH, A, C double bond O, OH, and we'll also form OH, BOH. And so we've managed to find the monomers from this polymer. A really important thing for us to know is that we can distinguish between addition polymerization and condensation polymerization, because only alkenes undergo addition polymerization, whereas for condensation polymerization we need either dicarboxylic acids and diamines to form polyamides, or dicarboxylic acids and diols to form polyesters. And so what we need to remember is that alkenes undergo addition polymerization, and then we have dicarboxylic acids and diamines for polyamides. So polyamides are a type of condensation polymer, or we could have dicarboxylic acids and diols to form polyesters, which is another form of condensation polymer. And so these addition polymers are these polyalkenes. So for example, if a question asked you, what would this molecule here undergo, what kind of polymerization, then because this is an alkene, this is ethene, that means it undergoes addition polymerization. Condensation polymerization is also when we remove a small molecule. So in these cases, they would be waters. So in this case, we would form waters. So waters would be liberated when we react dicarboxylic acids and diamines, or dicarboxylic acids and diols. So now we're going to have a look at some questions. So for question 1, a molecule which has the structure shown below is polymerized to form the biodegradable polymer known as PHB. For A, draw the repeating unit of the polymer PHB. So what we do is, to make it easier, we draw 2 of these molecules so we can kind of see how the condensation polymer is formed. So we have OH, and then CH3, hydrogen, and then we've got a CH2, and then you've got a carbon with double bond oxygen, and then OH, and then we're going to add another one of these. And then we plus ... and then on the other side as well be plus ... And so again, reminding you of condensation polymerization, we're wanting to remove waters. And so we liberate a water. So what we do is we remove this water here. And so this water is liberated. And that's why it's a condensation polymer, because we're liberating a small molecule. In this case, it's water. And so the polymer that we form looks like this. So we have oxygen, and then carbon with a CH3, and then hydrogen, and then CH2, C double bond O, and then now we have O, C, CH3, and then carbon with 2 hydrogens, and then C double bond O, O, and so on. Then remember, we have to add these trailing bonds to just signify that it goes on, and then we put a square bracket and then N. So this is our polymer. And actually this polymer is a polyester, and the reason we know that is because of this here. So this is an ester group. And so because loads and loads of these groups repeat along this long chain molecule, this is actually a polyester, which is a type of condensation polymer. And so to find the repeating unit of this, what we do is we start from the left. So I'm going to start from here, and then you scan along from left to right and see when it starts repeating again. And we can see that it starts repeating at this oxygen. And so we draw a line here, and this is our repeating unit. So we have the repeating unit is oxygen, carbon with a methyl group, and then a hydrogen, carbon with 2 hydrogens, and then we have this C double bond O, and then we have to draw the trailing bonds again, and so this is our repeating unit. And then for B, suggest a reason why the polymer is biodegradable. So remember, for polyesters and polyamides, they can be hydrolyzed. So this polyester can be hydrolyzed in acidic or alkaline conditions to reform the monomer. And this is because of this polar C double bond O bond. So we have carbon, which is delta positive, and it's bonded to this oxygen, which is delta negative, and so it can be hydrolyzed. And this makes it biodegradable. Before I move on to question 2, feel free to click off the video and try it for yourself first. So for A, the repeating unit shown represents a polyester. Name this polymer and give the IUPAC name for the alcohol used to prepare this polyester. And so first, this is a condensation. Because in order to form this polymer, we have got rid of some water. And then for the IUPAC name for the alcohol, first we need to remember that to form a polyester, we need a diol and a dicarboxylic acid. And so we can split up this polyester that we've got into the alcohol bit and the carboxylic acid bit. So if I split it here, then this section here will be from the dicarboxylic acid, and this section here will be from the diol. And so it's the diol bit that we want. And so if I draw this out, it is HO and then CH2, 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 and then OH, because after we split up this C double bond OO bond to get the dicarboxylic acid section and the diol section, we have to add the bits of water back on, and so we add these hydrogens back on. So this is the diol that we get. So then this diol would be propane 1,3-diol, because the 2 OH groups are on the first and the third carbons. And then for BI, so the repeating unit shown represents a polyalkene copolymer, and this copolymer is made from two different alkene monomers. So first we need to name the type of polymerization occurring, and so the other type of polymerization is addition, and this is when we add up loads and loads of alkene monomers to form a long chain molecule, which is a polyalkene. And then for 2, draw the structure of each alkene monomer. So what we do here is we split it up, and then we get rid of these bonds here and form double bonds instead. And what we get is carbon double bonded to a carbon, and then we have hydrogen, another hydrogen, a fluorine, and another fluorine. So this is one of the monomers, and the second monomer would be carbon double bonded to a carbon, and then we have 2 fluorines on this carbon, a CF3 on this carbon, and a fluorine. And so these are 2 alkene monomers. And then for C, one of these 2 polymers cannot be broken down by hydrolysis. Identify the polymer and explain why hydrolysis of the compound does not occur. So we know that polyesters can be hydrolyzed. And so the polymer which can't be hydrolyzed is the addition, the polyalkene. So it looks like this. Well, we'll just put the addition polymerization product. So this is the polyalkene. And this is because it has unreactive carbon-carbon single bonds and also carbon-hydrogen bonds, as they are not polar. And so they don't attract attacking groups. Whereas if we look at the condensation polymerization, we always get this C double bond O bond, which is polar because we have a partially positive charge on the carbon and a partially negative charge on the oxygen, because there's such a big electronegativity difference between the carbon and the oxygen. And so this is attacked by some attacking groups, and so can be hydrolyzed.